Right, so I've got all of the components blue tacked onto the robot now. And as you can see, I've added an addition. This is the HCSR04. It's a ultrasonic distance sensor, which can send out an ultrasonic pulse, measure the time it takes to come back, and then estimate the distance based on that. I bought mine off eBay for $1.99 with free delivery. So the way this works, it's got 4 pins, and I'm following a guide on modmypi.com, which I'll put in the description if you need it. And I'm connecting the VCC, which is the power, to my main VCC power chain, which I was using for the motor board in the previous video. And I'm also connecting the trigger pin to the Raspberry Pi, the echo pin to a different pin on the Raspberry Pi, and then the ground to the same ground rail that I'm using for the motorboard. The main difference with the previous videos is that I'm using resistors for this one as well. So let me go back to the video. Hopefully you can see this, but I've got two resistors attached to the power coming out of the Raspberry Pi. Sorry, going into the Raspberry Pi. So the response from the ultrasonic sensor goes back into the Raspberry Pi, and because the ultrasonic sensor takes a 5-volt signal, we need to change that via the resistors to a 3.3 volt signal before it goes back into the Raspberry Pi. Otherwise, it might damage the Pi. So let's have a look at the circuit diagram again. We've got, again, the power going to the ultrasonic sensor, the trigger, so the signal from the Pi going to the trigger pin on the ultrasonic sensor, and then the response going back to the Raspberry Pi. Now this guide recommends using pins 16 and 18 for the GPIO input and output. We've already used those in the previous video for the inputs for the motors and the outputs of the motors, sorry. So we're gonna have to use different ones. So what I did was I consulted this pin-out diagram again and tried to find some free GPIO pins, which are the black ones with the yellow squares in the middle. And I found that there were 2 I could use. I mean, there's a whole row here, so there's actually several you can use, but I chose to use GPIO 5, I believe, and let's see, was it 25? Let's have a look. Pin 22, which is this one here, which is GPIO 25, because that one was also free. So we've got GPIO 5, GPIO 25, which corresponds to 22 for the trigger pin and 29 for the echo pin. So let's go back to the diagram. This echo is going to pin 29, that's in sequential order from the top left, and the trigger one is going to pin 22. And remember, you've got to have this 1K resistor in between the echo and the Pi, and then again you've got 2K resistor between Pi pin and the ground pin. So let's just have another look at what that looks like on the board. What you've got here is the ultrasonic sensor. It's got the 4 outputs listed. You've got the ground pin, which is this yellow one here, going back to the board and onto the, if you can just about see it, the negative rail of this 5-volt power line, which we've used for to power the motors. Yeah, so we've got the positive terminal from this power chain, which is a 5-volt, and it's actually being used to power the motors. I'm also using this to go straight into the VCC pin, which is the top one, or this one here, which is brown in my case. And then the ground is going to the negative terminal on that same rail here. And then for the other 2 pins, we've got trigger and echo. They both go to the Raspberry Pi. Trigger goes directly to the Raspberry Pi, and that goes straight to, let me check again, pin 22 in sequential order, and the echo goes to the breadboard So I'm gonna have to say the ECHO, otherwise it's gonna trigger my Alexa. So the ECHO pin, which is the orange one here, goes to the breadboard, and then there's a 1K resistor on the breadboard, and then it goes back to the Raspberry Pi, which will give it a 3.3 volt signal, and that is the pin 29, which is this one here, and then it goes through 2K's resistors back to the negative terminal on the breadboard, on the power chain. Best thing to do, it's difficult to see that, but I'll upload the code itself and you can reference that, and also reference this diagram because it shows you where each of the outputs should be going. Just bear in mind that these GPIO pins are different for my code. And then the next step is just to actually write the program itself. I will show you that on my Pi. So I've called this file distance-test.py. You can see it in the bottom left there. So I'm going to type nano distance-test.py and go through this line by line. You need this top line because it defines it as a Python file. We need to import time and rpi.gpio, and then we declare the mode, the GPIO mode, as board, which means it's sequential from left to right, top to bottom. And as I said previously, we've got trigger 22, echo 29. That means the trigger signal is going to go into the board on the 22nd pin, and the response is going to come back to the board. Sorry, the trigger is going to go out of the board on port 22, and then the echo from the ultrasonic sensor is going to go back into the Raspberry Pi on 29. And this is what we're doing here. We are setting it up so that the trigger pin is an output pin, and the ECHO, sorry I can't say echo, oh, I just said it again. GPIO in is for the ECHO pin, so that that's set up as an input. And firstly, we'll make sure that the trigger output is 0, so it's not sending any data it's not sending any signal to the sensor. And we'll print this message saying we're waiting for the sensor to settle, and we'll sleep for 2 seconds. And then we've got this try loop, try while loop. What that does is it cycles through this while loop indefinitely until this accepts statement. So I'll keep doing this until you do a Control-C with your keyboard, which will interrupt it. And at this point, it'll do a GPIO.cleanup, it'll reset all the pins, and it'll print interrupted to the command line so you can see what's going on. And then while it's looping through this while loop, what we're doing is we're setting the trigger output from the Raspberry Pi to 1. This can be true or out, I think, or there's another way of defining it, but I put it to 1, which means that it sends a signal. It sleeps for 0.00001 second, and then it turns off the output. So it sends a very short pulse, and it says while the input hasn't received, i.e. while the ECHO input is 0, it will measure the start time, and then when the ECHO has been received, i.e. when the input is 1, it measures the end time. And of course the duration of the pulse is the end minus the start. And using that, we can use this calculation to work out roughly what the distance is in centimeters. We then print the distance to the terminal, and we sleep for half a second so that we don't just spam the terminal. You can again, I'll put this code on YouTube, so you can download it and either upload it or just paste it into this file. Click Control-X and it will prompt you to save if you've changed it. Once you've saved it, you can run it. Now if I type in Python distance-test.py, you'll see that it prints out waiting for it to settle, and then it starts reading. And if I move my hand in front of it, you can see that it drops. I'll show you me doing that. So what I'm doing is this, and you can see that the distance is dropping considerably. So it seems to be working. Now the next step, there are a few outliers there, like a 3000, that's obviously not meant to be there, so we might have to take an average, but it's a good start. If I press Control C, it says interrupted, and it's cleared the GPIO settings. So the next step is to mount this onto the board, onto the chassis, and start making some code which will allow it to drive around and sense walls and things like that.